Hi, we have already looked at the ideal diode model, and we saw in the previous video that the VI characteristic of a diode differs from the ideal VI characteristic. Okay, and therefore the logical next step would be to develop diode models that more closely represent the real VI characteristics of a diode, right? So let's do that in this video. So we said that the real VI characteristic looks like this, right? And this would be a good approximation. So an ideal diode model would be a good approximation of this characteristic if we assume that the voltages, the forward voltages that you are working with is much larger than zero point 0.7 volts, right? This gap between this line and the y-axis is 0.7 volts. So if we assume that we are working with, let's say, 50 volts or 200 volts, the power line voltages, things like that, then zero point 0.7 is very small, and then you can assume this to be almost zero. And if you assume that you are not reaching breakdown, then you can assume that this is ideal diode model, right? And that's the kind of model that we have discussed till now. But let's say you do not want to ignore that zero point 0.7 volts drop. Okay, you do not want to say that the zero point 0.7 can be neglected with respect to the voltages that you're using. Then what will you have to do? You could have a model which is just a straight line at this particular value, which is zero point 0.7, and then it's zero current all the way into the reverse bias. And let's assume that we don't go into breakdown, and therefore we can forget about the breakdown. Okay, so that kind of a model is what is called the constant voltage drop model. So in a constant voltage drop model, what happens is the diode, instead of being replaced by a short circuit when it is in the forward bias, is replaced by a voltage of zero point 0.7. Okay, what this also means is that the forward bias is only going to happen when V is greater than zero point 0.7. If V is less than zero point 0.7, we replace the diode with an open circuit. Okay, can you see the difference? In the ideal diode, we had the reverse bias when V is less than 0, but in the constant voltage drop model, we have the open circuit when V is less than 0.7 volts. All right, okay, so that kind of gives us the model for this straight line and this zero current here. You may then say, well, this is not really a straight line, is it? Even though it looks like a straight line, if you expand it and see, there is a small resistance here. There is a small slope here. It's not entirely vertical. There's a small uh, divergence from the vertical direction. So we can model this diversion as a resistance, and therefore we get the model here, the piecewise linear model. Okay, so in this model, the diode is going to be on again when V is greater than zero point 0.7. But along with the zero point 0.7 volts drop across the diode, you also get a resistance RD. So there is a forward resistance to the diode. This resistance will be very small, but it is there nevertheless. Okay, and then if the voltage is less than zero point 0.7, you just get a open circuit. Okay, so these could be three ways of modeling the diode depending on how much accuracy you want in your results, right? There is one more model which is called the small signal equivalent model, which is only used when we are looking at when the voltage across the diode is a fixed value but has small changes riding on that fixed value. Okay, and we will take a look at that model in one of the later videos.